Hi everyone, we are group 16 and the project is the passive thermal system design and analysis for OptCube 6x1 CubeSat. I am Kyle Chilla. My partners are Brendan Schulz and Ryan Fox. Our faculty mentor is Dr. Christina Lemmer and our student mentor is Max Bruel. For our agenda, we're going to start with our introduction, which includes a brief overview and some definitions and terminology. Then we'll move on to our success criteria for our project, and then the scheduled overview. Then we'll move on to thermal modeling, which includes our thermal budget, some modeling process, and some assumptions. And then we'll break down our model and look at the structure and the individual components. And then we'll go into the analysis we ran and go over the results. And then we'll go over the thermal management and control. And then we'll go over the different preliminary thermal control and all the different systems. And then we'll have our conclusion. WALI is the Western Aerospace Launch Initiative. We are an RSO with the goal of designing, building, and launching WMU's first satellite. The OptCube satellite will help develop new methods of diagnosing electric propulsion devices while on orbit by using optical emission spectroscopy. The satellite contains the optical emission spectrometer, the pulse plasma thruster, or the PPT, the attitude determination and control system, or ADAX, and the ES, which is the electrical power system, and then the onboard computer, or the OBC. Now on to our definitions and terminology. Some basic heat transfer definitions and terminology begin with conduction. Conduction is the process by which heat is directly transmitted through a substance when there is a difference of temperature. You can see from our figure there, we have our T2 is greater than our T1 and it's separated by a distance d. And the equation that it uses is Q dot is equal to a negative kappa, where kappa is the thermal conductivity times the temperature gradient times its area. Radiation is largely dependent on the object's surface area. And its equation is Q dot is equal to epsilon, which is the infrared emissivity, times the Stefan-Boltzmann constant, times its area, times the change in temperature. A couple other definitions are solar absorptivity, alpha. This is the measure of the ability of an object to absorb solar radiation. Then lastly, infrared emissivity, or epsilon, as we saw in the radiation equation, is an object's effectiveness in emitting energy as thermal radiation. Some basic space definitions and terminology. LEO is low Earth orbit, and that occurs at an altitude under 1,200 miles or around 2,000 kilometers. The beta angle is the measure between the solar vector and the orbital inclination. The solar vector is a vector connecting the center of the sun to the center of the Earth, and that changes during orbit. And it determines the amount of time the satellite is in direct sunlight. A beta angle of 0 maximizes the time spent in the umbra, and a beta angle of 90 degrees minimizes the time spent in the umbra. And the umbral cone is the overlap shadow cast by the Earth from the sun, as you can see in the picture there. Now moving on to our success criteria for our project. Our success criteria is to design a passive thermal control system that efficiently and effectively directs heat flow away from the sensitive satellite components so that the temperature of these components do not deviate from their design survival conditions over the lifetime of the entire mission. Passive thermal control systems will utilize static components to direct heat flow to the radiative surfaces. A conductive pathway is a pathway in which heat can flow from higher energy areas to lower energy areas. And a couple examples of a passive thermal control device is a thermal strap or multi-layer insulation, but we'll get deeper into that later on in the presentation. Now onto our schedule overview. Our project started off in the preliminary design phase. This started last semester and it went into January of this year. All these dates we set were flexible, so we had some room for error, and we did a lot of researching and planning into our project during this phase. Once this was completed, we went into the analysis phase. And this is where we did most of the hard work and all the modeling of the satellite in AutoCAD. We did a lot of experimenting with thermal control devices in the satellite structure to see which one worked best. Once we completed that, we were in our secondary design phase, and this involved going over our model and seeing if we had any errors or if there's any way we could improve it even better. We used our decision matrix to determine our software and the potential hardware we'll be using for the thermal control system. The software we chose was Thermal Desktop, based off of the effectiveness and accessibility and the ease of use. And then our hardware we're going to use is thermal straps in combination with multi-layer insulation. And those had the best effectiveness cost mass because there is a mass requirement of the satellite.
In this section, we will talk about the thermal modeling process, the thermal budget we had to work with, and the assumptions made in model design. The thermal budget outlines the environment each component can survive in, and also their operating conditions. These numbers drive the requirements for thermal control system design. Our low-end survival condition is negative 30 degrees Celsius with a high of 70 Celsius, and our low-end operating condition is 0 Celsius and a high is 50. And as you can see, that's driven by the optical emission spectrometer. Moving on to thermal desktop modeling. Since we required a model of the satellite in AutoCAD to use with the thermal desktop software, we first had to learn how to make these models. Each piece presented unique challenges which may alter the approach to the piece, but the basic steps, we would begin by making the base geometry of the satellite components, and then each piece of geometry would be assigned physical properties, and then we had to assign contactors, and there's either surface to surface or with geometric considerations. And where applicable, heat loads would be applied to represent internal components that produce heat. We'll talk more about those later in the breakdown of the internal components. And this is all very important because we must use radiation to expel excess heat. So the goal of the thermal control design is to move heat from areas that cannot radiate out to space to our radiators. Now I'm going to walk you through a short thermal desktop example. For this example, I placed 2 bricks of aluminum 6061 T6 next to each other. I added some more nodes for a higher model fidelity. And then I added surface contactors in the area where the 2 bricks meet. The next step was adding physical properties to the bricks of aluminum, and this menu on the left is for the physical, and the menu on the right is for radiative properties. This menu shows the basic orbit that I will be testing them at a beta angle of minus 23 degrees and at an altitude of 408 kilometers. I then applied a heat load on the smaller brick on the right, and this is a representation of the thermal model after the simulation has occurred. As you can see, the values on the left are all within a very small range because the heat applied was very high and the bricks were relatively large with a long steady state condition of 5,000 seconds. And it's from these basic principles that we were able to model each component of the satellite using the respective geometry and physical properties. For the history of our model, we began with a 1-node analysis. This was a simple aluminum sphere, and this proved to be a good first step for the team so we could all become familiar with thermal desktop. Next was the 8-node, which used basic shell geometry and gave a general representation of the satellite layout. And then we moved on to a 300-node analysis, which gave a higher fidelity structure and a better representation of the internal components. And so our thermal modeling process for the older models, we took measurements from SolidWorks and redrew them in AutoCAD. Then we added conductive pathways, and the initial analysis was completed. For the current model, the SolidWorks files were imported to AutoCAD where the geometry could be recreated using thermal desktop solids, and the components were made of the composite solid geometries that accurately represent the overall satellite geometry. Again, material properties and pathways were established, and this allowed for individual components to be tested and then imported to a master file. So the assumptions we had to make, we assumed that all components were going to be turned on throughout the simulation. And we also assumed that the component's power draw is the heat load on that component. Also, the plume from the PPT will not be considered as a heat source. Now for a breakdown of our thermal model. This is the structure of the satellite. It is composed of 6 aluminum plates and 2 end caps. The assumptions we made, we didn't include any bolt holes, and any small fillets smaller than 2 millimeters were ignored for model fidelity and decreased processing time. The structure is made out of 6061 T6 aluminum, and that comes in a black anodized for the outer structure and a clean version or a counterweight, which is the satellite. Here's a layout of the internal components. They each include brackets made out of aluminum. Starting from the bottom left to the top right, we have the EPS, OBC, and transceiver all on one stack, and then the ADAX, the PPT, and the OES. All right, moving to the internal components further breakdown. The EPS has a heat load of 0.15 watts and is comprised of aluminum 6061 T6 and a clean version. And it also contains PCBs that are less than 15% copper by volume. And the OBC and transceiver have a combined heat load of 0.48 watts and again use PCBs less than 15% copper by volume. The ADAX has a heat load of 5 watts, and again, aluminum and PCBs for the materials we use. And not pictured here are reaction wheels, which provide attitude control for the satellite. The PPT has a heat load of 1.5 watts, and it is made out of aluminum and PCBs. One note, the nozzle end is considered dirty due to plasma plume deposition. The OES produces 1.25 watts and is again made of aluminum that is anodized and clean for the internal. So here is our complete thermal model. Pictured in yellow are solar cells, which are placed on the outer portion of the structure. And this brings us to a total node count of 4,586 nodes.
Moving on to our thermal analysis. In this section, we will discuss the analysis scenario and the results. Most of the OpsCube's components are made of aluminum 6061 T6 and are either black anodized or cleaned. This changes the optical properties of the satellite, which directly affects how much radiation can leave. Since radiation is our only method in which heat can leave the satellite, it is important to have high emissive surfaces. These material properties are from a thermal desktop profile courteously provided to us by Mr. Jim Myers of NASA Glenn. For our orbital analysis, one case was analyzed with an altitude of 408 kilometers, a beta angle of negative 23 degrees, with 16 analysis points per orbit over the first 10,000 seconds. This 10,000 second transient time covers approximately the first 2 orbits, and due to the amount of processing time it takes to run this scenario, only the one case was analyzed. Further analysis will be conducted over the summer for a beta angle of 90 and a beta angle of 0. These 2 profiles will show the temperature extrema as they will maximize and minimize the amount of time that is spent in the sun. The figure on the right shows a representation of the orbital scenario in thermal desktop. Here we can see the satellite on its orbital path around the Earth, and then the umbral cone is shown in purple. The thermal desktop analysis results show that most of the components of the OpsCube are well within their operating conditions. The OES temperature, however, drops below its safe operating condition while in umbra. Moving on to thermal management and control. Thermal management in spacecraft is dependent primarily on conduction and radiation. Conduction is the primary method to move heat within the satellite. This can be done utilizing thermal control components to establish conductive pathways that allow for specific control heat transfer between two locations. The only way to release heat is through radiation on exterior surfaces. Highly emissive coatings allow for the maximum amount of radiation out of a satellite, and is dependent primarily on surface area, so controlling radiative surface sizing is important. The exterior of our satellite is black anodized aluminum, which has a very high absorptivity and emissivity. Our design is for a passive thermal control system, which uses static components to maintain optimal temperature ranges based on the thermal budget. The thermal control system is responsible for environmental interaction, which includes the radiation in and out of the satellite, as well as the local environmental heating. Since we're in low Earth orbit, we have a higher heating effect from Earth's albedo and infrared radiations. The thermal control system is also responsible for heat transport within the satellite and heat rejection out of the exterior surfaces. As stated previously, most components of OpsCube will be fine with minimal thermal control. This is because the structure was designed to efficiently reject heat away from those components. The cold spots will be addressed locally with MLI to keep their temperature within their operable ranges. Multi-layer insulation reflects heat internally between its layers and conducts the trapped heat away to other surfaces. This insulation is more effective with the more amount of layers that it has. However, most applications have between 3 and 6 layers. Moving to our conclusion, and then the next steps for the Wally thermal management team. From our thermal desktop analysis, we conclude that most of the temperature ranges for the components within OpsCube are fine over their first few orbits. This being with the exception of the OES, as it does go below its minimum operable conditions. These cold spots will be addressed locally using multi-layer insulation. The Wally thermal management team will be continuing with this work throughout the summer and into the coming fall. During this time, the model will be reviewed and improved, and a thermal control component sizing will be finalized and reviewed. Localized solutions for thermal control will be implemented into the thermal model as well. At this time, we would like to extend our gratitude to the following people, without whom our project would not have been possible. Dr. Christina Lemmer, a professor here at Western Michigan University, Max Brummel, a mechanical engineering graduate student here at Western, both of whom were advisors for this project and helped us along through the last 2 semesters. The University Nanosatellite project reviewers, who have helped guide us through with their review process. Mr. Jim Myers of the NASA Glenn Research Center. Mr. Myers taught the team valuable thermal modeling skills and processes, as well as offered his insight and expertise in thermal modeling and analysis using Thermal Desktop. We are grateful for the time and assistance provided to us by Mr. Myers. Cullimore and Ring Technologies has graciously provided the Wally thermal management team with 3 licenses of their software, Thermal Desktop. Cindy Beer, Director of Sales at Cullimore and Ring Technology, provided the team with these software licenses. She's been extremely helpful in explaining the fundamentals of the software and has offered direct assistance on many occasions when the team has encountered problems. Thank you all. We appreciate your time and your effort. And now we would like to open the floor up to any questions.
Okay, guys, thank you very much. Now the presentation is open to the question and comments. Please unmute your mic and ask the question, or you can type your question in chat room. So meantime, I will ask a question, guys. What is the most, let's say, challenging part of your project?
The most challenging part for us would have to have been the working on the computers remotely, since we only had a few licenses for Thermal Desktop that were located in the lab. We had to remote into our computers most of the time, which could provide just network issues or other software problems. We also had some licensing issues in the beginning of the semester. And then just verifying that our models were correct, being that we're relatively new to thermal modeling.
Okay. Anybody wants to add anything?
Yeah, I'd like to add something. Definitely going into a new software and not knowing too much about the thermally model process had a pretty steep learning curve. And so once learning that and getting in the groove of Thermal Desktop, once we got into it, it was good. But like I said, it had a steep learning curve.
Okay. Thank you, guys. So any question to our presenter, please? You can unmute your mic and ask the question. We still have a few minutes for question and answer. So I will ask one more question then, guys. Nobody will be volunteering now. So what do you learn? What do you learn from this project? Each of you, of course, which you haven't learned from your classes.
I can start off on this one. A lot of this was based on basic heat transfer, and I'm actually in heat transfer right now, but it definitely helps solidify a lot of the concepts from the class and help apply it to a real world problem that is just a little bit different from the view that we get inside the classroom. I think that really.
Okay, thank you. Next, guys.
Definitely something I learned was the whole thermal radiation in space. That was something that didn't really learn in my heat transfer classes, and it was kind of a new thing to learn. So that was one of the things. But basically, the entire culmination of all our schooling kind of came into this, all our time management, project planning, all that. So there's a lot of ways where we saw it come into play.
Okay, thank you, Kyle. Brandon, you want to add something?
Yeah, definitely. So with this, something we didn't really use in classrooms, especially for heat transfer classes, we didn't really do any software application. We talked about and discussed softwares, but actually using a software to calculate thermal properties and temperatures on orbit through different scenarios is just something a bit different, taking like a geometric approach rather than just a pencil and paper approach to things.
Thank you, guys. So this is the last chance to ask the question, guys. Anybody in the audience wants to ask a question, please go ahead. Okay, guys, I don't think so anybody's asking the question. So thank you very much for the presentation. I also want to thank the audience. We have 26 of them. Thank you very much for your time and listening to our presentation. So the next presentation would be at 4 p.m.